Relative velocity. Let's say my sister is leaving on a train trip, and I am standing by watching her go by on the train. We'll assign right to be the positive direction. The train is moving to the right at 7 meters per second relative to the ground. We'll call this velocity vector vtg, with t referring to the train and g referring to the ground. My sister is walking toward the front of the train with a velocity of 2 meters per second relative to the train. We'll call this velocity vector vst, with s referring to my sister and t referring to the train. What if I want to know how fast my sister is traveling with respect to the ground outside? Let's call this vector vsg, with s referring to my sister and g referring to the ground. Vsg would be equal to Vst plus Vtg, which is 2 meters per second plus 7 meters per second, which equals 9 meters per second. Walking toward the front of the train, my sister is moving 9 meters per second with respect to the ground outside. What if my sister was walking at 2 meters per second toward the back of the train? Since the right is our positive direction, that means that her velocity vector with respect to the train would have a negative value, negative 2 meters per second. To find her velocity with respect to the ground, we use the same equation, Vsg equals Vst plus Vtg, but this time Vst equals negative 2 meters per second, so our answer is 5 meters per second. The key to working relative velocity problems is to be consistent with the way you write your velocity subscripts. For example, the velocity of our train with respect to the ground was written as vtg, with t referring to the train and g referring to the ground. So when you write these, have the first letter in your subscript refer to the moving body, and the second letter refer to the frame of reference, or the object that your moving body is moving with respect to. In our example, Vtg equals the velocity of the train with respect to the ground. Vst equals the velocity of my sister with respect to the train. And Vsg, the velocity of my sister with respect to the ground, equals Vst plus Vtg. If you're consistent with the way you write your subscripts, then the first subscript letter on the left side of your equation will be the same as the first subscript letter on the right side of your equation. And the last subscript letter on the left side of your equation will be the same as the last subscript letter on the right side of your equation. This train example is an example of one-dimensional relative velocity, since all the velocity vectors point along the same line. Let's look at a classic two-dimensional example. I drive my boat across a river that's 2,000 meters wide. The velocity of my boat relative to the water is 5 meters per second in a direction perpendicular to the current of the river. The velocity of the water relative to the shore is 2 meters per second. Part A, what is the velocity of my boat relative to the shore? And part B, how long does it take for my boat to cross the river? Okay, so what are we given? I'm driving my boat across a river that's 2,000 meters wide, so that will be my displacement. Let's set up and to the right to be the positive directions, so that my displacement is x equals a positive 2,000 meters. The velocity of my boat relative to the water is 5 meters per second, and it's in a direction perpendicular to the current of the river. So let's call that vector VBW, B for boat and W for water. Next, the velocity of the water with respect to the shore, which we will call VWS, is 2 meters per second. We draw this upward in the positive direction along the river. Next, what are we looking for? Part A asks us for the velocity of my boat relative to the shore. We will call this VBS. B for boat, and S for shore. And part B asks us for the time it takes for my boat to cross. So now we need an equation for part A. Since we wrote our relative velocity subscripts in a consistent way, we know that VBS should equal VBW plus VWS. We can draw VBS as a vector to see how we'll find a value for it. From our vector drawing, we see that we can use the Pythagorean theorem and that the magnitude of VBS squared equals the magnitude of VBW squared plus the magnitude of VWS squared. We next solve this equation for VBS. Next, we can plug in our known values of VBW and VWS. Then we use our calculator to solve, getting a value of 5.4 meters per second. This is the magnitude of our velocity vector. Now we need to find a direction. To do this, we look at the angle that our velocity vector is pointing. It's pointing at an angle theta east of north. To find theta, we use this trigonometric equation utilizing the magnitudes of our other two vectors. Then we solve this equation for theta. Next, we plug in our values, and using our calculator, we get an angle of 68 degrees east of north. So our complete answer for part A is that the velocity of the boat with respect to the shore is 5.4 meters per second in the direction 68 degrees east of north. Now for part B. How long does it take for my boat to cross the river? We only need to worry about the direction across the river to the right. Velocity is displacement over time, so we can use this equation. We just solve this equation for t. Now we plug in our values for x and VBW. Our calculator gives us a value of 400 seconds for the time it takes to cross the river. Remember, for problems involving relative velocity, be sure to be consistent when you write your subscripts, and it will make the problems go a lot easier.